to continue our discussion on the shell energy balance. And let's take a look at another example, which is heat conduction with a chemical heat source. So we'll have heat conduction. Let's say you have a packed bed plug flow reactor that looks like the following. So you have, cylindrical tubes, and within this packed bed reactors, only the area packed with the catalyst should the reaction happen. And let's call it the reaction zone here. So reaction zone. Okay, so it's going to be packed with catalyst materials. And before is we'll have two inert zones before and after that reaction zone. So inert. And we would have defined dimensions. So we have the R direction, radial direction, and the Z direction. And we will have reactants be coming in from here. So reactants. And let's call the entrance of the reaction zone being Z equals to 0. And the end of the reaction zone being Z equals to L. So basically we can define zone 1, 2, and 3, which is the inert, the reaction, and the other inert zone. And outside the inert zone will have products coming out, okay? So a little bit more definition on the system so we can make some assumptions and simplify things, okay? So first, this would be a packed bed and plug flow reactor. So plug flow meaning that there's no velocity distribution. The velocity is going to be the same everywhere. So basically that means no R and Z dependence of V sub Z. And the second assumption is that the reactor wall is well insulated. So reactor wall insulated. That means that the temperature would be independent of R. So it's not going to change in the radial direction. So that makes our life much easier now. And then let's say that, in the reaction zone, you're going to have chemical reaction heat, right? So you're going to have chemical reaction heat. Chemical reaction heat. And for simplicity, let's call that heat being SC, which is equal to some SC1 constant times F of the dimensionless temperature distribution. Okay, so let's say for simplicity, where you have this symbol here being the dimensionless, maybe it's called theta, I'm not sure. This is the dimensionless temperature. Which equals to T minus T naught over T1 minus T naught. And what are T naught and T1 and T? So here, the T here is the local temperature. Okay, so it's assumed to be equal for catalyst and fluid. And we have T naught and SC1. These are empirical constants. Empirical constants. for given conditions. Inlet conditions, let's specify that. So T1 is the inlet temperature. Oh, sorry, T0, and T1 is going to be temperature at negative infinite. Okay. Okay, so with these defined, let's go ahead and do a shell energy balance. But before we do that, again, we need to determine how we define the shell. So from our previous example, you probably have some idea or some hint how a shell should be defined. And here is my takeaway. My takeaway is that you will like to define the shell, typically the thinnest part of the shell being parallel to the direction of the energy transfer, okay, or being parallel to where temperature will be changing. So in this case, we will be expecting that as your reactant flows over the reaction zone, you're going to have a chemical reaction occurring. So the temperature should be changing in the direction of the z direction. So if I were to, to give a guess where how the shell should be defined, I will make a guess that the shell should be having a very thin shell like that in the delta z, or in the z direction. Okay? And that's because that's the direction where the temperature is changing and where the energy is going to be the direction of energy transfer or transport. So with the shell determined, we can now try to perform our shell energy balance. So let's write that down. So oops. My apologies. My laptop, or sorry, my tablet kind of does this all the time. So shell energy balance. And we already defined the delta Z, right? So we need to figure out the volume of the shell. The volume of the shell would be what? Would be pi r squared times delta Z. So the cross-sectional area times the thickness of the shell. Volume of shell. So to perform our shell energy balance, we know that at steady state, the energy coming in would be what? The energy at steady state, there's no accumulation of energy. So we have 0 on the left-hand side, which equals to the energy coming in. We're going to use, again, the combined energy flux vector. So E, Z, and Z times its cross-sectional area, pi r squared, minus EZ at Z plus delta Z, also times the cross-sectional area. But now we do have a generation term. So we have generation of energy from the chemical reaction. So we're going to have to add it up. So add the volume of our shell times the energy term from the chemical heat source. So times SC, which is defined previously. Okay, so again, this is in minus out, and this is generation by chemical reaction. Now let's divide all by pi r squared delta Z. Pi r squared delta Z. What we get is the following. We get EZ and Z minus EZ and Z plus delta Z over delta Z equals to SC, negative SC. So if delta Z approaches 0, we get dEZ dZ equals to SC. Okay, so that's the first important conclusion we have, is that the change in the combined energy flux vector as a function of position is exactly equal to the energy produced per volume by the chemical reaction. Okay, so again, if we revisit the combined energy flux vector, we would have what we have, the convective energy transport term plus delta H times Vz, convective, and we have heat, and we would have work by shear stress, right? And again, let's analyze this one by one. Okay, so again, if you look at the shear stress part, we have tau V equals to what? Equals to, let's do this, tau Z R VR plus tau Z theta V theta plus tau ZZ VZ. Again, there's no velocity in the R nor in the theta direction, so we're left with tau ZZ VZ, which equals to negative mu 2 partial VZ partial Z times Vz. Again, the velocity doesn't change with position. This is a plug flow, so this term is 0. So there are no work associated with fluid motion here that needs to be taken to consider. Okay, now let's take a look at the convective transport part and the heat. So let's continue our discussion right down here. Okay, so if you look at the convective transport part, again, let's take a look how that can be analyzed. Okay, so first, let's say EZ equals to 1/2 rho V squared plus rho H Vz. And we can expand the conduction term as K dt dz. Now, the H part, the enthalpy part, can actually be written as this. So this equals to some reference plus rho Cp times the actual temperature minus that reference temperature, T0. We'll put it up here. Okay, and so you can see that this is a scalar. Okay, and this is a scalar. So if you analyze this by taking the derivative, let's analyze derivative, because that's what we're going to get, right? Derivative. We have dEz dz equal to what? Equal to dz times 1/2 rho V squared times Vz. And this is 0 because Vz doesn't change with Z, and inside the parenthesis, everything is 0. Now, let's continue. Plus dz times H0. Again, this is a scalar, so this is 0 times Vz plus dz times rho Cp T minus T0. Now, T is a function of Z, so this this is not going to be 0 again. So this term stays, right? And then finally, we have the conduction part, which is negative k dt dz. Okay. So here we are with the terms left. So this term stays, and I forget the ddz part. This term stays. So after our analysis, we get the following. Finally we get to our final analyzed part. So dez, dz, after checking each term, the terms are left would be what? Would be the conductivity term, so d squared t dz squared plus rho cp v naught dt dz equals to sc. Okay, so this is the this is the result of the shell energy balance, and what's left at the end would be the conduction term and the convection term here equals to the generation term. Okay, so to continue our discussion, we're going to discuss the problems from zone to zone. So we have 3 zones, right? Zone 1 and Zone 3 are the inert zones, and Zone 2 is the zone that has the catalyst where the chemical reaction occurs. So if you look at our final equation, in Zone 1 and Zone 2, there are no chemical reactions. So if we write this down, so for Zone 1 and 3, actually, we only have this following term. We only have the convective transport equals to the conduction. Okay, this is for the inert zones. And the inert zones meaning that z is smaller than 0 or z is larger than L. But for Zone 2, we do have the chemical reaction. So z is between L and 0. We have rho cp v naught dt dz equals to k effective d squared t dz squared plus sc. Okay, so we have 2 governing equations, one for Zone 2 and one for Zone 1 and 3. And now let's look at the boundary conditions. 请进。哎，你好。
现在忙吗？
没关系，我暂停一下可以的。我在上课而已。Okay, so our next step is to first figuring out the boundary conditions at each zone, okay? So let's go ahead and try to do the analysis. So boundary conditions. So first, at z equals to negative infinite, we have T in the first temperature in the first zone, or Zone 1, equals to T1. This is based on our initial definition. And at z equals to 0, we know T1, T in Zone 1, so the temperature should be continuous, so the temperature at Zone 1 should equal the temperature at Zone 2. And also, at z equals 0, the heat flux should also be continuous. So the heat flux is the effective thermal conductivity times the temperature gradient in Zone 1 will equal to the heat flux in Zone 2. Okay, so this is, we can call this the continuity of heat flux. Okay, and then at Z equals L, again we have the continuity of temperature and heat flux between zone 2 and zone 3. And finally, at Z equals infinite, we will simply say that the temperature is finite. Okay, so now we have the governing equations in blue and in red written down, and the boundary condition written down. Let's further do some hypothesis or simplification, right? So in most cases, or in most practical applications, the convective terms are usually way more important than the conductive term. Okay, so we will drop out the conductive term. I'll write that down. So for practical applications, in plug flow reactors specifically, the convective terms are way more important than the conductive terms. So we will drop the conductive terms. Okay, and also we would like to introduce a dimensionless coordinate. So we will introduce dimensionless coordinates, capital Z equals to Z over L. So now we can define a dimensionless heat source. Which is N equals to SC1L over rho times T1 minus T naught times CP V naught. So after we define all these dimensionless terms and drop out the convective terms, here are our governing equations again. So at zone 1, so Z is smaller than 0, we have the following. We have the gradient of the dimensionless temperature over the dimensionless Z. Let's probably put a bar here just to make sure we don't confuse ourselves. Equals to 0. Okay. And then at zone 2, where Z is between L and 0, or Z naught or Z bars between 0 and 1, we have dH dZ bar equals to the dimensionless heat source here. And finally, at zone 3, where the dimensionless Z is greater than 1, we again have dH dZ bar equals to 0. And the boundary conditions become what? Becomes like this. So when z equals negative infinite, we have the dimensionless temperature in zone 1 equals to 1. When z equals to 0, we have the dimensionless temperature equals in both zone 1 and zone 2. And when z equals to 1, we have zone 2 equals to zone 3. Okay? So we're not going to solve everything for you, but just to show you how it's going to be done, we are going to solve, and we say that if the temperature in zone 1 equals to constant C1, then we have the following conclusions. So the integration of f times dh equals to n times z, and then also we have the temperature in zone 3 equals to zone 2 equals the temperature at zone 2 and z equals to 1. So if we draw a plot, this is how it would kind of look like. Okay, so basically you have zone 1, 2, and zone 3. So this is zone 1, zone 3, and zone 2. And this is our dimensionless temperature. This is z over L, 0, 1. So here's what we get. So we have 1, and this is a log scale, by the way. So we have something that looks like this. So if the reaction is exothermic, meaning that, you know, n is a positive number, then we have a temperature accumulation as we go downstream, or temperature increase as we go downstream. If we have an endothermic reaction, exothermic and endothermic. Okay, so maybe we would have a homework assignment. Maybe it would be a problem 10b18. We might give you this homework assignment for you to actually figure out how this is solved. Okay, so our second discussion, or discussion about heat conduction with a chemical heat source, will probably end here, and we will continue with looking at forced and free convection heat transfer in the next part.